Good afternoon, everyone. Thanks for coming. My name is Sriharsha Kandala, and I'm a software engineer with the Climate Modeling Alliance at Caltech. So, a quick intro about us. We're a group of climate scientists, software engineers, mathematicians working on developing what's called an Earth system model. So, this is a joint collaboration between Caltech, MIT, and JPL. So these Earth system models use a lot of parameterizations for various pieces like clouds, turbulence, convection schemes, etc. And based on the quality of these parameterizations, this can result in uncertainties in climate models. So the objective is to use update these parameterizations based on global observations and targeted high resolution simulations so that we can produce really accurate climate simulations. Our software stack is built in Julia, and we support distributed GPU and CPU simulations. I'd like to thank our sponsors. So this is a quick snapshot of the subset of our ESM software stack that contains the climacoupler. There are multiple levels to that. At the bottom, we have this basic building blocks like ClimaComps, which provides those device specifications and the communications interface. We have the ClimaParams, which provides the physical constants, the universal constants, and other constants. Then we have the thermodynamics package, which provides us the moist thermodynamics relations. At the next level, we have the ClimaCore, which provides the spatial discretizations for our simulations, the needed infrastructure for the spectral elements and the finite difference. Similarly, we have the Clima time steppers, which provide the time stepping code. Then we have the RRTMGP, which provides the radiative fluxes. Then the cloud microphysics, which provides those cloud parameterizations. And then the surface fluxes, which provides the interface fluxes at the Atmos land and Atmos ocean interfaces. At the next level, we have this climaatmos.gl, which is essentially the die-core, which builds on the packages in the lower levels. Then we currently prescribe ocean temperatures and sea ice concentrations, but the plan is to eventually use Clima Ocean from MIT coupled with that. And then we have a Clima land and a simpler approximation of a bucket model for the land model. And then the coupler couples the die-core, ocean, and the land model. So a quick look at the dynamical core. We essentially solve the conservation equations for the mass, momentum, energy, and transport. The radiative fluxes and the source stems fit into these equations from the various source packages. So a quick look at the discretization. We use a hybrid grid for our spatial discretization. We use the spectral element discretization in the horizontal direction, and then we extrude the spectral element grid in the vertical direction, and then we use staggered finite difference approximation in the vertical direction. And our grid is a pancake-like grid, which is stretched in the vertical direction. We use generalized coordinates and we use covariant velocity components. We have like a high aspect ratio mesh, and we use horizontal explicit, vertical implicit time stepping for our production cases. In the horizontal, we use hyperviscosity for stabilizing the horizontal momentum, energy, and tracer transport equations. For the turbulence and convection schemes, we have a simple boundary layer diffusion scheme, also called the Sriharsha scheme, and then we have our EDMF model. So a quick look at the horizontal discretization. We use what is called a HP mesh. Here H stands for the outer mesh, and P is the degree of polynomial approximation within each element. So we have the sample spectral element mesh with 4 spectral elements in here. So here with the continuous Galerkin spectral element method, all the degrees of freedom on the interface of any two elements are redundantly represented. And then once we discretize the spatial equations using Galerkin projection, the details are not that important for the talk, but we will eventually end up with a term that looks like this: mass times the derivative is DSS of RHS, where the right-hand side is completely can be evaluated completely local to a spectral element, and thereby completely local to a given process. So the major communication cause for this algorithm comes from the direct stiffness summation. So we have this pure direct DSS, the normal DSS, where we just add up. So in the picture, you can see the local degree of freedom numbering for each of the local spectral elements, and the corresponding global numbering in green, which needs to be the same at the end of each simulation, because this is like a C0 continuous approximation. So what we need for our case is this M inverse, approximately the M inverse times direct stiffness summation of the RHS. So, and there is a nice property that when we use the quadrature grid to coincide with the physical grid, we can have a reduced up count when evaluating this combined operation. And it essentially reduces to a Jacobian weighted average at each of the redundant degrees of freedom to compute the G. So all of our communication infrastructure is stored in our topology data structure. For example, on the right, there is a picture with about 16 spectral elements and partitioned with a space filling curve across 4 processes. So the topology data structure contains all the information needed for the communication infrastructure. For example, it contains the partition information. It stores the process neighbors for each of the processes. Then for local elements, it classifies them into fully internal elements and elements called perimeter elements, which exist at the boundary with elements from other processes. It also provides information on the interior and ghost faces and interior and ghost vertices, and it also stores the data for the representative ghost vertices, the number of unique faces and vertices that needs to be communicated to each process neighbor, etc. And this also contains the information needed for constructing the indexing arrays for loading and receiving the send and receive buffers for the DSS. So the next item is the graph communication context, which we have in ClimaComps. For example, here is a data structure which contains the persistent send-receive graph communication context. So we first build the connectivity graph from the topology information. For example, in our case, it's a continuous Galerkin. So vertex connectivity is what determines if spectral elements are connected to each other. For example, in this data structure, we have the send. So we store the send and receive ranks for each of the processes and the corresponding send and receive buffers. We tend to use the DSS inside a time loop. So to minimize the overhead, we use persistent MPI communications as a default. We also support non-persistent communications, and this works with both the GPU and with the CPU and GPU buffers. And in case the MPI is not CUDA aware, it does some internal buffering, which is a bit more expensive. So here's a quick snapshot of our graph communication infrastructure for the DSS. So we have a start where we post the sends and receives, and then we have the finish where we use a wait out statement to make sure the receives happen correctly, and then we do an optional probe in the middle using the progress. So the first stage in this DSS is actually building the DSS buffer. So it's built based on the information provided from the topology data structure. So it builds the transformation signature for the perimeter array. So since in our case we use local coordinate systems for each of the spectral elements, and we store velocity on a covariant, we store the covariant velocity. So for the vectors, we need to first transform it to physical velocities before we actually apply the DSS. So that's some extra work involved with the vectors. So the DSS buffer classifies the fields into scalar, covariant, and contravariant bins for the transformation purposes. For the vertical component, given the construction, we do not need to do the transformation for the 3D velocities. And then we build, the DSS buffer also builds the perimeter data array on which the DSS results are actually stored. It builds the indexing buffers for loading and unloading the communication buffers, allocates the send-receive buffers, and initialize the graph communication context. So our weighted DSS algorithm is split into 3 pieces to enable communication computation overlap within a given DSS. The first part is the weighted DSS, where we fill the buffers and start the communication. Then we do the internal DSS while the communication is happening, and then do the ghost DSS after the communication is finished, which gives us this overlap, the communication computation overlap. So the first piece is the weighted DSS start. This piece weighs and transforms vector fields to physical fields as needed. So this calls the DSS transform on the perimeter elements first, and the results are stored in the perimeter, on just the perimeter elements, and the results are stored in perimeter data. Then we compute what is called the local part of the weighted DSS on the ghost vertices using only the information from the process local vertices. So this helps us reduce the size of the communication buffer a bit. And the results are stored in each of the local vertex locations in the perimeter data. And then we fill the send buffer and initialize the communication. The second piece is the weighted DSS internal. So we transform now, while the communication after the communication has been initiated, we apply the DSS transform on the internal elements, and then store the results on the perimeter data, and then we do the DSS on the local vertices and faces. And in the third phase, we finish the communications. We add data from the receive buffer to the corresponding location in the perimeter data. So for the ghost vertices, the data is only added to the representative vertex, and then the data is sent from the representative vertex to all the redundant vertices. So, and then we untransform the data as needed for the DSS and store the result back in the original field. And for running this on the cluster, there are some additional considerations. For example, unlike CPUs and the GPUs, we need to make sure the local MPI, each local MPI rank picks up a different GPU. Sometimes all ranks tend to pick up GPU 0, and that gives, for obvious reasons, really bad results. So we need to make sure it picks up, each local MPI process picks up a different GPU on the node. And then we also need to bind MPI ranks to NUMA domains. When you assign multiple threads to a GPU, we need to bind the CPU threads in the NUMA domain to this GPU, otherwise it can be inefficient. So this is a quick representative workflow for a normal DSS. So we first set the device. We can set the device to CPU or GPU, and we also support single-threaded and multi-threaded CPUs for the device. Then we set the communications context. Here it's the MPI communication context for distributed simulations. Otherwise, it can be a singleton communications context. Then we go through the usual process of building the domain, the mesh topology, space, and then the fields. Then we build the DSS buffer, and then in the time loop, we can just evaluate a DSS at each time step. At each of the time, first we do all the local operations and then apply DSS, and this happens every time step, and sometimes every stage of the time step. So coming to we did some preliminary scaling studies. So we have an aquaplanet simulation with cloudy sky radiation, a Frierson diffusion model. We did both 0 and 1 moment cloud microphysics, and we used the strong stability preserving not time stepper. We use horizontal resolutions from 55 kilometers to 13 kilometers. We use 64 vertical levels. The simulations are done on Deraco supercomputer at NCAR. It has a total of 8 nodes with about 4 A100 GPUs per node. We used simulations with processors in the range of 1 to 256 GPUs for this study. So we see these are the strong scaling results for this simulation with the zero moment microphysics. We see that the scaling efficiency is in the higher 90s, up to about 300 horizontal elements per process. 3,000 horizontal elements per process, after which the scaling efficiency could drop down. That seems to be a good size at which the GPUs are relatively saturated. So on the left, we have SYPD versus the number of GPUs. SYPD is the simulated years per day versus the number of GPUs. And on the right, we have the scaling efficiency versus the number of GPUs. So a quick summary. We built this portable interface which provides the communications interface for all the components in our at system model stack. We see good, strong scaling results on the GPU from our preliminary runs. In terms of outlook, we would want to try to increase the overlap between when computing multiple DSS on multiple fields to see if that further increases the scaling efficiency. And we also want to explore the model where currently the current model places each GPU on a separate MPI process. We want to explore the model where we can place multiple GPUs, or to be specific, a full GPU node and a single MPU process, and run multiple processes. Yeah, thank you.
Great, thank you very much. And again, in the interest of time, I think the next speaker can already set up everything, and we have time for a question.
Well, thanks for your talk. I just have a question, like why are we reporting strong scaling on multiple GPUs while kind of what we experience is like usually on the GPU there is a specific optimal problem size that works well, and then from then it makes more sense to go with a weak scaling?
We wanted to look at both the strong and weak scaling numbers. We just started the scaling study, and this is like the first. For the weak scaling, we see close to 100%, but we didn't do the weak scaling study yet on the cluster. We just did it on a local cluster with 4 GPUs or so, but we need to extend it to the to Deraco.